Okay, today we're going to be thinking about a current carrying wire in a magnetic field. So last time we considered if we had a wire and that wire has a current going in it, it's going to have a magnetic field. And we looked at this is our current and this is our magnetic field. Now the magnetic field will be right round this whole wire. This is our magnetic field. And we looked at the right hand grip rule to determine the direction of the current and what the magnetic field lines would look like around that cable, like around that wire. Now, because this wire now has a magnetic field wrapped around it, it's like a magnet. And if we were to take, so we had 2 bar magnets, and we were to bring them beside each other, you'd be able to feel the force repelling these 2 magnets. Similarly, if you had one that was sort of south and this was north, you'd feel that those forces attracting each other, because when you bring 2 magnets together, the fields interact. So if we now take a magnetic field, so here's north, here's south, and the field lines go from north to south. Now in this magnetic field, let's say we put a wire, and this wire has a current, and in this current it's going to be coming into the page. So it's coming, if you remember when we do it, if we draw an X on our wire, that means it's going into the page. If we were to draw a wire and we put a wee dot, by convention that means that it would be like the current would coming out of the page towards you. So we've got this wire and it's got a current flowing through it, and as a result it's going to have a magnetic field. Let's draw our field lines around this magnetic field. So using our right hand grip rule, the magnetic field would be in that direction. So now we've got a magnetic field round our wire and we've placed it inside a magnetic field between these wires, and what's going to happen is it's going to distort our magnetic field. And I'm going to give it around here, and there's going to be a force, just like when if you take your 2 bar magnets beside each other, you can feel them either pushing away or pulling towards each other. There'll be a force here, and the force will be in the downward direction. It'll be actually perpendicular, as if it was kind of going through the paper, but if it's 2-dimensional we can't draw that. So we'll have this direction of force. And it's important to realise that the magnetic field of the magnets, the magnetic field of the direction of the movement of the current, and the direction of the force, they're all perpendicular to one another. The force exerted by the magnetic fields acts on the charged particles. Now this is true whether it's electrons or protons, it doesn't matter what type of charge the particles have. When you've got charged particles flowing, they produce a magnetic field, and it's the interaction between these 2 magnetic fields is felt on the charged particles, and if you were to take a piece of wire and put a current through it, place it in a magnetic field, you'd be able to see that wire move, and that movement comes from the force that's been exerted on the individual charged particles as they flow through that wire. Now, the rule for how to work out the direction of everything is called the left hand rule. So we've had the right hand rule. This is now going to be the right hand rule. So this is what it's like. If you've got your magnet, you've got your wire. So if you take your right hand and put your thumb and the two first fingers perpendicular to each other, thumb sticks up, that's the direction of the force. Your first finger is the magnetic field and your second finger is the current direction. This left hand rule is for positively charged particles moving in an magnetic field. And we call this the Fleming's left hand rule. And it was invented by Sir John Ambrose Fleming, who was an English electrical engineer and physicist. If we're investigating for negative charge, we point the second finger in the opposite direction to the charge movement. This has a lot of implications, and we can use it to control the flow of charged particles flowing through a magnetic field. It's the principle in which particle accelerators are built on. If let me just get this up a bit. Say in the past, you had, for televisions used to work with cathode ray tubes. So you would have this tube, and there'd be your screen, and you would have magnets, and then you would have here a particle electron generator, and it would fire some charged particles. And then you would use this magnetic field here. You would change its intensity. You would be an electromagnet, so you could have it going from changing the polarity. This go north, this south. Then you could flip the polarity, and by doing that, you can move the particles where you want it. And that's how it was this principle in which televisions were first, when the televisions were first invented, that they used a cathode ray. So this is called a cathode ray television, and that's how they operated. Televisions, flat screen TVs today use a completely different technique. You'll still see a cathode ray in oscilloscopes. Still use them, and particle accelerators. Oops, let me spell particle. Particle accelerators, which we'll talk about in the next section. These still use this principle of having your electromagnets, which you can change the polarity, the intensity, and that directs this flow of electrons, or it could be ions or protons, to where you want them to go. The force that is applied on these charged particles will also cause an acceleration, and the velocity, and So that all can be controlled by controlling these magnets. And then if you want to do further maths, what you would do is you would combine the velocities of the particles, and you would use vector equations so that you can work out the different velocities, where they're going to go and what's going to happen as the charged particles move through the cathode ray. So I hope that helps.